let's talk specifically about an oscillating mass spring system. So first off, if you remember, when we talk about springs, there's two main equations we've talked about before. One of them is Hooke's law, which describes the force that a spring exerts on an object. This is called Hooke's law. The force that a spring exerts is equal to negative kx. The negative sign describes that the force that the spring exerts on an object is always opposite the direction the spring has either been compressed or stretched. So for example, if I have a spring and it's just hanging from some sort of hook up here, it has a natural unstretched, uncompressed length. So this is an equilibrium state for the spring. But if I decide to hang a mass from the spring, because the mass has weight, the mass will pull down on the spring. If I hold the mass and let the system come to equilibrium, if I think about the free body diagram on the mass of course has the pull of gravity, the weight of it, so mg, but the spring is pulling upwards with this magnitude of force of kx. So x in this equation represents, from this original equilibrium position of the spring, how far the spring has been stretched, in this case, downwards. And so that's what the x in this equation would mean when we're talking specifically equilibrium. Now, as a reminder as well, K is called the spring constant, also sometimes called the force constant of the spring. That is something unique to the spring. So it's a relation of how strong the spring is. The bigger the K value, the stronger the spring is. K has units. The units can be written either as newtons per meter, which, if we think in terms of force needs to be in newtons. X is a distance, a stretch, or compression, so if that's in meters, K has to be in newtons per meter in order for the force to come out to be in newtons. But because a newton is a kilogram meter per second squared, this is also a kilogram per second squared. So either unit, whether we use newtons per meter or kilograms per second squared, it's valid either way. So in terms of figuring out how strong a spring is, we can use this equilibrium situation because X is something we can measure. We can measure how far a spring is stretched out when we hang a mass from it. So we could say that this mass itself, that magnitude of force upwards from the spring, has to equal the force of gravity if we're in this equilibrium situation. So if you remember, equilibrium, we mean net force of 0. We also mean net torque of 0, but there's no turning or twisting going on here, so we don't need to satisfy that equation. And so we could calculate what K is by knowing the mass of the object we're hanging from the spring. We know G, that's 9.8 meters per second squared, and then X, how far the mass was stretched, the spring was stretched. The other equation we have for a spring is the potential energy that the spring stores because of the stretch. We call this specifically elastic potential energy. So as a reminder, we use a capital U to represent potential energy. We came up with this equation by integrating force, and that left us with an equation of 1/2 kx squared to represent the amount of energy stored by a spring when it is stretched or compressed. Now in the test notes, you're going to also see this as 1/2 ks squared, because our author used S to represent a generic direction, whether we're stretching in the Y direction or the X direction. It is common to see it as X as well. Now, in terms of talking about oscillations, mathematically, it's easiest to walk through the equations if we talk about a mass spring system on a horizontal surface. Now we're going to talk ideal oscillations still first, meaning no thermal energy being generated, so there's no friction involved of any sort. Now, of course, that's not terribly realistic, but we start with the ideals and can build on the ideals as we go. So if I have this mass connected to the spring, if I have equilibrium, meaning there's no net stretch or compression of this spring, nothing would be happening right now. The mass would just stay connected to that spring. It would sit there at rest forever, essentially. So in order to get oscillations to occur, I'm going to just draw the picture below. I have to somehow put energy into this system. An easy way to do that would be to pull the mass to the right, which in turn stretches the spring, and now we have potential energy, this elastic potential energy that we did not have initially. So potential energy was added in this case. Now, granted, I could easily push the mass to the left and compress the spring, and that would be another way in which potential energy could be added. I could somehow tap the mass and make it move and give it kinetic energy. As a reminder, kinetic energy is the energy of motion, so capital K. As long as there's some sort of motion, there's kinetic energy in the system. So in this ideal situation, I'm going to slide this up a little bit. As soon as I release the mass, it's going to start moving to the left because the spring is pulling on it. The spring is exerting a force to the left. Now, in the equation for force, that negative sign means the force that the spring is exerting is always opposite in direction to the stretch or compression. So since this spring was pulled to the right, the force from the spring is to the left. Had we compressed this spring over here towards the left, the force would be to the right. And so that's what the negative sign in that force equation represents. Now, the spring force is not the only force. There's, of course, a normal force. There's a force of gravity. But because we're talking about motion along a horizontal surface, the normal force and the force of gravity are not doing any work. And so in terms of talking about the net force on this block equaling mass times acceleration, so Newton's second law, if you recall, because of the nature of vectors, we had to add the forces in just the x direction to determine the acceleration in the x direction. we had to add the forces in the y direction to determine the net force in the y direction, and thus the acceleration. Because the motion is on a horizontal surface, there is going to be no acceleration in the y direction. There's no motion at all in the y direction. And so this essentially tells us that the normal force has to equal mg. In the x direction, in this particular case, we have simply that force from the spring pointing towards the left. So that force of the spring is solely responsible for the acceleration that this block experiences in the x direction. As x changes, so as this block moves, this distance that the spring is compressed is getting smaller. At a moment in time, it will be 0, but then it continues to the left, and that force will get bigger and bigger. And so this acceleration is constantly changing. Now, if we think back to our generic equation of motion, so A, amplitude, the maximum distance the mass is pulled from equilibrium, the amplitude is essentially determined by me. I'm the one that's grabbing the mass, pulling it to the right. However far I pull it to the right is the amplitude. So this is the maximum distance to the right or left from equilibrium. And I essentially choose that by pulling the mass or compressing the mass, the distance I choose. Omega is the angular frequency, so the number of radians per second, the oscillation rate of this mass on the spring. Phi naught is a phase shift to make sure our equation is satisfying the initial conditions that we have. In the case here specifically, where I pull the mass to the right, so the maximum positive distance, and I release it from rest, my graph of position versus time would start at a maximum positive value. The mass would move towards equilibrium, past equilibrium to its maximum negative distance, and so forth. So the phase shift would be 0 in this specific case. We could say that x is exactly a cosine omega t. All right, so if x is a cosine omega t, then if I take the derivative, I find that the velocity is negative omega a sine omega t. Derivative of a cosine is negative sine. The derivative of I don't remember the term, but the stuff inside the cosine term, the omega t is omega. And so we get this function for v. If I take the next derivative, I'll get the function for a. I end up negative omega squared a cosine omega t. If I come back to this Newton's second law, showing us where it is the spring force that is causing the acceleration, I'm going to go ahead and plug in this equation that describes x. X is changing. It is not a constant. We have here what we call a differential equation. A is the second derivative of this position with respect to time. So we have a function that relates this position to the second derivative of that position. The result of that is this cosine function here. So plugging in for x, the function that we have that describes the motion, and similarly plugging in for a, the second derivative of that same function. When we plug these in, notice that the a omega t is in both terms. It's on both sides of the equation. So I can cancel that out. It doesn't mean the system's not oscillating, of course. This mass on a spring, if I've pulled it to the side and put energy into the system, it's totally going to oscillate. But mathematically, this relationship shows us that K, the spring constant, must equal the mass times omega squared, the angular frequency of this mass spring system. So this tells us that omega is the square root of K over m. The rate at which this system is going to oscillate, the mass oscillating back and forth, is determined by how strong the spring is, so that spring constant, and then how much mass is attached to the spring. So this is unique for an ideal mass spring system that's going to oscillate. It turns out this equation is valid if the mass spring system is oscillating vertically as well. So if I had hung the mass from a spring and pulled down or lifted it up and let it go, the system would oscillate at this number of radians per second. If you remember, in a previous video, we were talking about omega being 2 pi f, but f is 1 over period. That means period is 2 pi over omega. If I plug in omega, I find that I could write this period as 2 pi. I'm going to bring the square root up. When I do that, I end up with the square root of m over k. So the period, as a reminder, is the number of seconds for one oscillation. So the amount of time to oscillate is directly related to the mass and inversely related to the spring constant. This is unique to the mass spring system. And it's unique in this assumption that we have an ideal mass spring system. One other thing to keep in mind in this ideal situation, if there's no thermal energy created, then the total mechanical energy must be conserved. Meaning any potential energy and kinetic energy in the system at any one moment in time is the same as that amount of energy at a later moment in time. So the total energy is constant. There will be times where the potential energy is all that we have. So for example, in my picture, when I said I pulled the mass to the right and I'm going to release it, well, if I pulled it to the right, that split second before I've released it, all of the energy is in the spring. If we think about the energy equation for a spring, instead of x, I'm going to put a. Because again, I'm the one choosing the amplitude. Amplitude means the maximum distance from equilibrium. So however far I've pulled it to the right is the amplitude. So if the energy in this system at this moment in time is all potential, I can write that as simply 1/2 Ka squared, because it has to be at its maximum distance for the energy to be completely potential. There's going to be moments in time when the energy is all kinetic. That means there's no potential energy. Well, the only way to have no potential energy is for the spring to not be compressed or stretched, meaning equilibrium is zero. So the energy is all kinetic energy at the moment the mass is moving through that equilibrium position. And we could write that kinetic energy as 1/2 mv squared, where v is the maximum possible value of speed. At every other moment in time, there will be some potential energy and some kinetic energy. 1/2 mv squared. The spring, if it's stretched or compressed, even just this small distance, it has some potential energy, but the mass will still be moving at that moment. And so there will be some of both types of energy. As we look at oscillating systems, if we want to relate position and velocity, with the mass spring system, we can totally use conservation of energy, or we can use the equations that describe the motion. Both are perfectly valid, both are useful, but ultimately, we want to remember that energy is conserved. We still want to remember how we can write the equations that describe the motion as a function of time. And then uniquely, we find that omega for a mass spring system, the radians per second, the angular frequency, is the square root of k over m. So how fast this system will oscillate is directly related to the spring constant and the mass. And then if we use our equations that relate omega to frequency and period, we can write the period in terms of mass and spring constant as well. So I'm going to do a few example videos of example problems and conceptual questions, but I will do that separately, so you can go through those separately.